Gravity is so familiar that it can feel almost invisible. A glass slips from a table and falls. Your body has weight. Rain drops toward the ground. The moon stays near Earth, and Earth stays in orbit around the sun. These everyday facts seem simple because we live inside them constantly, but they are signs of one of nature's most important interactions. Gravity is the attraction between material objects, and it acts wherever mass and energy exist. It is not limited to Earth, and it is not only about things falling downward. It reaches across space, shaping motion on every scale. Its effect becomes weaker with distance, but it never truly disappears. That combination makes gravity unusual. It can seem gentle in daily life, yet over enough time and distance, it becomes the force that organizes worlds, stars, galaxies, and the visible structure of the cosmos. The universe would look radically different without gravity. In the early cosmos, matter was not spread perfectly evenly. Some regions contained slightly more material than others. Those denser regions had a stronger gravitational pull, so they attracted more gas and matter. This created a feedback loop. A small concentration became larger, and the larger concentration pulled in even more. Primordial hydrogen gas gathered inside gravitational wells, many of them shaped by dark matter, which does not emit light but still contributes gravity. As gas clouds collapsed, they became denser and hotter. Eventually, the pressure and heat at their centers became intense enough for nuclear fusion to begin. That is how stars were born. Gravity did not simply act after the universe already had structure. It was one of the main reasons structure emerged from the early cosmic fog in the first place. Once stars existed, gravity continued building at larger scales. Stars gathered into galaxies, and galaxies gathered into groups and clusters. A galaxy is not just a collection of stars floating near one another by chance. It is a gravitationally bound system. Stars orbit within it because gravity constantly bends their paths, preventing them from simply moving away in straight lines. Dark matter appears to play a major role here as well, adding gravitational influence that helps explain how galaxies hold together and how large-scale structures grow. Across the universe, galaxies arrange into a vast cosmic web, with dense filaments and enormous voids. That web is gravity's handwriting written across space. It works slowly, but with billions of years available, small attractions become giant architecture. Every galaxy cluster is evidence that gravity is patient, cumulative, and powerful over cosmic time. For many practical situations, gravity is described by Newton's law of universal gravitation. Isaac Newton showed that any two bodies attract each other, and the strength of that attraction depends on two things: their masses and the distance between them. More mass means stronger pull. More distance means weaker pull. The weakening follows an inverse square pattern, meaning if the distance doubles, the gravitational force becomes 1/4 as strong. This idea was revolutionary because it connected ordinary falling objects with the motion of the heavens. The same principle that pulls a stone toward Earth also helps explain why planets orbit the Sun. Newton gave gravity a mathematical language that could predict motion with extraordinary success. Even today, for spacecraft trajectories, engineering, and everyday physics, Newton's description is often accurate enough to be the most useful tool. But Newton's theory does not fully answer what gravity actually is. It describes the force very well, but it leaves gravity looking like an invisible pull acting across empty space. Albert Einstein changed that picture in 1915 with the general theory of relativity. In Einstein's view, gravity is not simply a force pulling objects together. It is the result of curved spacetime. Mass and energy change the geometry of space and time, and objects move according to that changed geometry. A planet orbiting a star is not being dragged by a hidden rope. It is following a path through spacetime shaped by the star's mass. This is a strange idea because it makes space and time active participants rather than passive background scenery. Gravity becomes less like a push or pull and more like the shape of the road everything must travel on. One common image for general relativity is a stretched sheet with a heavy ball placed in the middle. The sheet curves, and smaller balls roll along curved paths around it. This picture is not perfect, because real spacetime is not a two-dimensional rubber sheet, but it helps show the core idea: mass changes geometry, and geometry guides motion. Einstein's theory also shows that gravity affects time. Clocks closer to massive objects can tick differently from clocks farther away. This is not just an exotic detail from deep space. Satellite navigation systems must account for relativistic timing effects, because even tiny differences in clock rates can produce meaningful errors in location. General relativity reveals gravity as something deeper than everyday weight. It connects motion, measurement, distance, and time into one framework, where the shape of spacetime determines how matter and light behave. The most extreme known example of spacetime curvature is a black hole. A black hole forms when mass is compressed into such a small region that gravity becomes overwhelming. Around it lies a boundary called the event horizon. Once something crosses that boundary, there is no path back out, not even for light. This is why black holes appear black. Light from inside the event horizon cannot escape to reach an observer. But black holes are often misunderstood. They do not automatically suck in everything in the universe like cosmic drains. From far away, a black hole's gravity behaves like the gravity of any object with the same mass. The extreme effects happen close in, where spacetime curvature becomes severe. Black holes matter because they test our understanding of gravity under the most intense conditions nature allows. On Earth, gravity is experienced mostly as weight. The force points approximately toward Earth's center, pulling objects downward and giving them the pressure and heaviness we feel every day. Weight is different from mass. Mass is the amount of matter in an object, while weight depends on the gravitational field acting on that mass. A person would have the same mass on the moon but would weigh much less because the moon's gravity is weaker. Earth's rotation slightly modifies the gravity we experience because rotation produces centrifugal effects. Local geography, altitude, and latitude can also create small variations. Still, for ordinary life, gravity feels steady and dependable. That steadiness shapes our assumptions about movement, construction, balance, and direction. What we call down is not an absolute feature of the universe. It is the direction local gravity pulls. Gravity also shapes the movement of water on Earth. The most familiar example is tides. The moon's gravity pulls on Earth, and because the pull is slightly stronger on the side facing the moon than on the far side, Earth's oceans deform into tidal bulges. The sun also contributes, and when the sun, moon, and Earth align, the tidal effect can become stronger. Tides are not simply the moon dragging water around in a crude way. They result from gravitational differences across Earth, combined with Earth's rotation, ocean basin shapes, coastlines, and seafloor geography. Gravity also helps explain surface water waves, because when water is lifted or displaced, gravity pulls it back toward equilibrium. The result is motion that can travel across the surface. Every shoreline is therefore a place where gravity's quiet influence becomes visible in rhythm and motion. Gravity contributes to weather as well. Air has weight because gravity pulls on the atmosphere, and that weight creates pressure. Atmospheric pressure changes with altitude because there is less air above you the higher you go. These pressure differences help drive winds and influence how air masses move. Warm air can rise, cooler air can sink, and gravity helps shape the vertical structure of the atmosphere. Rain also depends on gravity. Droplets grow inside clouds until air currents can no longer support them, then they fall. Weather is far more complex than gravity alone, involving heat, rotation, moisture, and sunlight, but gravity is part of the basic stage on which all of it happens. Without gravity holding an atmosphere to the planet and giving air and water weight, Earth's weather systems would not exist in the form we know. Life on Earth has also adapted to gravity. Plants use gravity as a directional signal through a process called gravitropism. Roots usually grow downward, helping anchor the plant and reach water and minerals, while shoots grow upward toward light. This is not accidental. plant cells can sense orientation relative to gravity and adjust growth patterns accordingly. Animals are shaped by gravity too. Bones, muscles, balance systems, blood circulation, and posture all develop under constant gravitational load. When astronauts spend long periods in microgravity, their bodies begin to change because the usual demands are reduced. Muscles weaken, bones can lose density, and fluid distribution shifts. These changes reveal how deeply life assumes gravity's presence. Gravity is not just a physical condition outside biology. It is part of the environment living systems evolved to interpret, resist, and use. Despite its everyday familiarity, gravity remains one of the great unfinished problems in physics. General relativity describes gravity beautifully at large scales: planets, stars, galaxies, and black holes. Quantum mechanics describes the behavior of matter and energy at tiny scales with extraordinary success. But the two theories do not yet fit together completely. Scientists are searching for quantum gravity, a framework that can describe gravity using quantum principles. This matters most in extreme situations, such as the earliest moments of the universe or the interior of black holes, where intense gravity and tiny scales meet. A successful theory could help unify gravity with the other fundamental interactions in one deeper mathematical picture. That is why gravity is both familiar and mysterious. We feel it constantly, calculate it accurately, and still do not fully know how it works at the deepest level. Gravity is the invisible thread connecting the ordinary to the cosmic. It makes objects fall, gives bodies weight, holds atmospheres and oceans to planets, moves tides, guides the growth of plants, and helps shape weather. At the same time, it gathers gas into stars, binds galaxies, curves spacetime, and creates black holes. Newton showed that gravity could be expressed as a universal law of attraction. Einstein revealed it as the geometry of spacetime. Modern physics now asks how it fits into the quantum world. This is what makes gravity so remarkable. It is the force we know most directly through experience, yet it still points toward the biggest unanswered questions in science. Every orbit, wave, raindrop, star, and galaxy carries the same message. The universe has shape because matter attracts, spacetime bends, and gravity never stops working. If you found this helpful, please like this video and subscribe for more explainers.